Hi, I'm Rabia Reba. The topic of my talk is acquiring process knowledge in hybrid planning domains using machine learning. I would like to start with a brief overview of the hybrid planning domain. As we know, automated planning, or simply AI planning, is one of the major capabilities of an intelligent system. It enables the system to solve a problem or achieve a goal based on the plan generated by the planning system. A planning system is logically separated into two parts: planning engine and domain model. A planner depends on the domain knowledge to apply techniques accordingly. Therefore, the quality of plans are quite affected by the effective engineering of the domain knowledge. In this dynamic world, realistic problems involve both discrete and continuous changes with nonlinear time limits and external events. Therefore, a planning agent must be able to interact with continuously changing quantities to generate up-to-date plans. Due to the limitations of classical domain for modeling realistic problems, hybrid domain models have been supplemented by two main components, which are processes and events. In comparison with classical domain, a hybrid domain involves time-dependent discrete continuous changes in the numeric resources. The key extension of hybrid domain is the ability to express temporal behavior in terms of the initiation and termination of processes. A process occurs continuous changes on numeric variables, which can be initiated and terminated by an action or by an event. Although hybrid domain has the potentiality to model real-time systems, but it arises some issues during the creation of domain models with process knowledge. For instance, it is hard to know the specification in advance, like feature selection, their dependencies, and model selection with appropriate approximation. Besides, the process knowledge may need to change over time, which makes it difficult to keep the domain up to date by hand. In that case, it will be better if they are automatically learned and adjusted in the system. Besides, the existing domain learning systems do not support hybrid domains. This paper focuses on utilizing machine learning techniques to automatically refine and improve hybrid domains. Specifically to acquire process knowledge defined in the hybrid domain. The main objective is to improve the domain model in terms of dynamicity and versatility. For instance, learning the process model from simulated or historical or real-time dataset can make the process model dynamic. Also, updating the learning dataset can enhance the dynamicity of the planning domain. Besides, adding new dataset with new features can make the planning domain versatile. For example, y may have relationship with other x variables, so it enables a planning domain to adapt many other different features automatically. Our proposed approach is the learning of process knowledge for modeling continuous effects. To effectively model the process or the continuous changes, we emphasize on applying statistical modeling using regression analysis. A regression model is used to infer the relationship between two or more variables. It estimates the outcome variable based on the predicted features. Steps of our proposed approach are shown here. Step 1. Input time series data. Step 2. Select the outcome variable y, whose values are to be predicted or estimated by the predicted variables x. Step 3. Conduct Pearson R-test to measure the correlation between each variable in order to find out feature dependencies. Step 4. Conduct VIF test to confirm the interdependencies between predictor variables, which is called multicollinearity. Step 5. Based on the Pearson R value and VIF test, the corresponding regression technique will be decided. Some of the techniques are simple linear regression, stepwise regression, or ridge regression in case of multicollinearity. Step 6. After applying the corresponding regression technique, we will get a regression model with appropriate approximation. In that way, we can select effective features and eliminate unnecessary features from the model in terms of beta values. For instance, if any x does not have impact on the resulting model, then we will set the corresponding beta value to 0. The final step is the deployment of the resulting model in the hybrid domain. Here is an example of the generic process model with PDDL plus semantics. To illustrate the feasibility of our method and to evaluate it on a real planning application, we use the PDDL plus encoding of the urban traffic control domain and the coffee domain. As a case study, we have exploited the UK Research Council funded Simplify project. In Simplify, a hybrid planning-based traffic control system has been introduced to handle the vehicle flow in both regular and unexpected road situations. This approach has incorporated a simple description of the vehicle flow process called flow run green, which took no account of the changing features of the road network. The learned regression model of flow run green process changes the turn rate value based on different learning factors such as green time, enter time, incoming or outgoing road saturation. As another case study, we have formulated the PDDL plus version of the coffee domain, which is partially inspired by its original PDDL 2.1 version. In the original PDDL 2.1 formulation, the only continuous change function is temperature, which is declared statically to get a generic cup of coffee without considering the brewing time. We exploit the coffee data, which shows that both brewing temperature and brewing time have a vital influence on the coffee yield, which defines the taste of the coffee. The PDDL plus formulation with learned process model generates plan according to the expected yield by regulating the brewing temperature and brewing time. To evaluate our proposed approach on the traffic domain, we check the simulation accuracy of the learned and original model using the same set of problems, then compare it against the EMSON output. Figure 18 illustrates the turn rate error comparison between learned and original model with the turn rate observed in EMSON. The result shows that the learned model improves simulation accuracy and produces less error as compared to the original domain model with static turn rate. To demonstrate the efficiency of the learned model in plan generation, here we have taken a simple planning problem. That is, reduce the congestion in this specific road. The result shows planner takes less time to solve the problem with the learned model. To evaluate the learned process models on coffee domain, we have simulated 4 different plans according to the expected yield. Figure 11 shows the bar graph displaying coffee yield at different temperatures, where error in percentage is the difference between the actual and predicted yield. The overall evaluation demonstrates that the learned model is more rational and closer to the actual process model. It provides more accurate simulation without statically declaring the continuously changing knowledge. In a nutshell, the learned process model can lead to higher quality plans. We can conclude that although hybrid domain models have enhanced the potentiality of applying hybrid planning in real-world applications, but still it is hard in terms of modeling continuous changes and their effects, also measuring the continuous process variables to control a process. The proposed approach automatically learns estimates, and encodes the continuous changes in the process modeling to improve the hybrid planning performance. Besides, it helps to choose effective process parameters and removing the irrelevant ones. Also automatically acquires the model of interdependencies between continuous variables. That's it. Thank you for your attention.